Hello, my name is Kaiser Bravo, and today I will be presenting on cross-correlation breakdown of BC420 plastic scintillators. So some introduction and motivation behind this work, sustained fission chains in assembly, and the ability to detect events are of interest in nuclear nonproliferation, safeguards, criticality, safety, and emergency response. And the tool that we use for this is cross-correlations. However, the focus of cross-correlations will be on the Langevin approach to interpreting Californium source-driven noise analysis, which has previously been shown to not adequately estimate subcritical neutron multiplication factors. And this is due to this approach being based on detection of first neutrons. But with cross-correlations, we can quantify how often neutrons begin the coincidence gate. This work will focus on how we analyze the simulated cross-correlation breakdown of lithium-6 glass-faced BC420 plastic scintillators to evaluate subcritical neutron multiplication models. So some background on cross-correlations. Once again, they're used to look at multiplicity and identify spontaneous fission. There are 4 interactions possible for our detectors: neutron-neutron, neutron-photon, photon-neutron, and photon-photon. Each correlation has a time difference, delta t, which is the difference between the time in the start detector and the time in the stop detector. This figure shows an example of a photon-neutron interaction, which will have a negative time. The focus of this work is based on the benchmark of a planar assembly machine with 293.1% enriched uranyl nitrate filled Winco tanks using a Californium source and 4 BC420 plastic scintillators. The figure shown here, there are 2 detector pairs, 310 and 1724, with 310 being the furthest and 1724 being the closest to the Californium source. And since we are focusing on Californium-driven measurements, we will be using MCPX Polimi for its built-in Californium source. Our first case is 2 detectors separated at 100 centimeters using a Californium source, and then the planned assembly as shown before for both filled and empty tanks. The simulated collisions and detectors are then processed using MP Post to obtain the cross correlations and pulse height for each scenario. The results are then compared in 3 ways: only source particles, only particles from multiplication in the tanks, and then all particles possible and collected. The figure 4 shows the cross correlations with the photon-photon outweighing all other correlations, and the neutron-neutron being the lowest, regardless of source. And then the bottom shows just single particle detections with photon, once again, being magnitudes more than that for the neutron. And the purpose of these 2 results are to show that overall that Californium is heavily underweighted by the multiplication, which produces the majority of the particles. However, as the separation continues, as shown here, the number of neutron-neutron correlation events detected decreases severely up to the point for detector pair 17 to 24, around 35 to 40 centimeters, that it stabilizes, and the majority of results come from the Californium source, which it is closest to. And some results continued. This is a comparison of the empty tanks to the full tanks for both detector pairs 310 and 1724. As such, we can see that the photon-photon is once again the most prevalent regardless assembly, but specifically in the multiplying assembly, that the frequency of neutron-neutron correlations are lowest regardless of assembly. And then all assemblies that these wings in the photon-photon region appear, and they are most likely due to inelastic fast neutron scatters in the detector and contribute to these appearances at these photon region times. Future work is to analyze assemblies at lower criticality and determine the contribution of alpha N reactions in uranyl nitrate. The impact of this work is an increasing understanding of subcritical assemblies for better material accountancies and anti-smuggling. Specifically, we will be able to understand better multiplicity models, which will in turn help criticality safety studies. I'd like to thank MTV for allowing me to collaborate with Oak Ridge, as well as Los Alamos over these years, and this has driven me to continue my career into graduate school. Here are my references. Thank you for your time.